starting the live stream to see if things work out fine. Let me see. Yeah, it's working out. That's good.
We have 10 participants here. Seems like it's live now. Good. Yeah.
Yeah, it's live. I put it live so that I made sure that things were working fine, not last minute.
I really was worried by not being able to access until the last minute. I thought there was a problem. Do you hear me?
Yes.
Yes.
Yeah.
Okay.
So I think we wait a few more minutes. I think because the keynote starts at 2:15 and we wait for her, for Sabrina, and because for the introduction we have very couple of slides. At the moment, some people are asking for links. Okay, shall we start?
So Shaka, I think we can start perhaps. And while we're waiting for Sabrina.
Yeah, I think so. We can start. At least we have 5-6 minutes to connect.
Mm-hmm. Yeah.
Okay. So let me see. So okay, you have to enable screen sharing.
Oh, I see. Let me see. All participants. We can share. Oh, okay. I can make you host. All right. Can you do it now?
Yes, just give me a second. I think it should be possible now. Okay, I think it should be ready now. Yes.
Yeah, we can see it.
So shall we start, I guess? Because I
think so.
Because Sabrina, I think she said her keynote starts at in 10 minutes, in 5 minutes. So I think she will join later on. So maybe we can continue. Okay, so let's start then. Yes, so welcome everyone to this second edition of Quantum Software Engineering Workshop. So together with my colleagues Rui and Tao, we are organizing the second edition of this workshop. And given the circumstances, unfortunately, this time will be virtual as well. And yeah, so just to start with few statistics. So this year we got in total 10 submissions, and we decided to accept 8 papers after 3 reviews from the program committee, and believe that that all the papers were really good in this time. So it means that that's why we have quite high acceptance rate, because they're quite really good pieces of work that we received this year. Rui and Tao, feel free to join anytime you like to join in. And then we would like to thank our PC members. And this is a list of our PC members who did a very good job in providing reviews on time and very thorough reviews to the authors of the paper. And now I will just go quickly to what we have in the agenda. So today we have this welcome that we are doing it right now. And then after that, we have a keynote by Professor Sabrina from University of Helsinki. And this will be about 1 hour. And then we take 5 minutes break, and then we will move into our first session on modeling. And in modeling, we have 3 papers that we will discuss. First is about density metrics for classical and quantum software designs, modeling quantum circuits with UML, and towards model-driven quantum software engineering. Then we will have about 10 minutes break, and we will go to the last session of today, which is on search, in particular related to quantum search. And we will have 2 papers. First one on experimenting with discrete time quantum walk, and the second one on generalized quantum tree research. So this is here we conclude today. And Then tomorrow we will start with our second keynote by Professor Ming Cheng Ying, and it will be from 1 o'clock. So please note the difference in time today. So today we started at 2, but since he is located in Australia, so we have to adjust the time a bit so that he can join us, because it's already too late for him, like 10 p.m. So he still nicely agreed to give the keynote at his late night. So, and then we will start with our session on quality, which will be covering 3 papers. First one is about identifying bug patterns in quantum programs, some size and structure metrics for quantum search, and then we will have a final paper on collection of reproducible bugs in quantum algorithms. And that we will discuss these 3 papers in this. And then followed by this, we will like to have some open discussion where we have a few points to discuss with all the participants, and everyone is feel free to join us this workshop. And note that we are doing this for most of the people, it's available live on YouTube, and only the presenters have given access to Zoom. But if you want to participate in any of the discussions more extensively, we suggest that you should contact us with your email address and affiliation so that we can let you in Zoom, and we will send you the Zoom link. And if you have any questions, you can also post them on YouTube channel, and we will take them after each talk. But we will prefer that we will only let people who are presenting to be connect through Zoom, because it will help us to avoid or strange incidences that we want to. That's why we want to control it. But we welcome you to join in Zoom if you are interested in participating in discussion. But you have to send me, Rui, and Tao an email, your name and affiliation, and we will send you the link and let you in. So that's how it's going to work, because I see that some people have some problem accessing it. But please feel free to contact us if you want to participate in discussion. Otherwise, you can also leave your questions in YouTube as well. So from this, so we will have a first keynote today by Sabrina, and she's going to talk about learning to measure, a new approach to variational quantum algorithms for near-term quantum computers. But we have to see if she has connected. Yes, she's here. Yes.
Yes,
Right timing. Perfect timing, Sabrina. So please go ahead.
Hi, everyone. Thanks. I will start sharing my screen. I just need a few minutes to do this operation.
Sure, take your time.
Okay, just a minute. Oops, mistake. I have to use the meeting ID, which is this. Oh, maybe I can do like this. Let me see if you can see my screen soon. I have to, sorry, I'm having a moment of difficulty, but meanwhile, so I will need a few more seconds because I'm trying to close my current presentation. I was in another presentation and I will close it now, and I'm starting again. Just a moment. Let's hope it works. Now we will need to connect via your meeting. But I don't have a meeting ID. I only have a link. Let's see if I can manage.
I think you can just share the screen.
Oh no, because it's actually a Prezi video. So it's I would need the meeting ID, but I will try just to do it via this link.
I see.
Okay, no. Maybe I can find it. Maybe did you send me the meeting ID of the? Oh, maybe. Let's see. Meeting.
I'm here.
Oh, sorry. This is Siri. Okay, I think I should be able soon. Let me see. Okay. Now I change it to my Prezi camera. And okay, probably you should be able to see it. Do you? Hello?
Yes.
You should. Oops. Okay, here we are. So probably what you would need to do is, if you don't see me full screen, to pin my video. Can you? Do you see the presentation
Yes.
full screen?
After you pin it. After you select the pin option, I can see you full screen.
Yeah, so now it is full screen.
Yep.
Okay, we managed finally. Okay, apologies for this little problem, because I was giving another presentation before and there was a switch, but thanks for your patience. So the presentation I'm giving today is called Learning to Measure, Adaptive Informationally Complete POVMs for Near-Term Quantum Algorithms. And this might be something scary because the title is so long, but I will try to give a very broad overview of the topic and of the main result that I'm going to introduce. So I will try to be as didactical as possible. And I will begin by considering the people who have created this result. So I want to introduce the researchers behind the result I'm presenting, and this is formed by a collaboration. So it was the Finnish team that are in between University of Turku and Algorithmic, our startup, and the IBM Quantum team in Zurich, led by Ivano Tavernelli and composed of Francesco, Panos, and Guglielmo. So I think that everything began in one of our excursions in the Qiskit world, that is the world of IBM QExperience, in the Qiskit Camp Europe, where our team started to investigate what can we do with quantum computers that exist nowadays, so with noisy quantum computer. If to understand and to put this in framework, I would say that in the very, very general perspective, the goal that nowadays we have in quantum computing is really to understand if and to which extent it is possible to build computing machines which are able to perform tasks really, I could say, impossible, but any classical conventional computer. So this is an overall question that, with the rise of the quantum ecosystem is becoming more and more, upstream or more and more explored. And while we do know that quantum algorithms, especially that are defined really as algorithm exploiting quantum properties, exist and that are outperform classical algorithm. At the same time, we also know that generally, when we think in terms of the most famous quantum algorithms like Grover search algorithm or, for example, Shor algorithm, generally we assume that they run on ideal fault-tolerant quantum computers which do not exist yet. So, of course, this is in the spirit of universal quantum computers, which is actually really historically also how people started to think in terms of quantum computing. And however, they soon realized that the whole concept behind, or the whole connection with quantum physics was related to the fact that because information is physical, and physical realization of quantum computers are becoming to be available, then also algorithms should be considered as somehow some small little experiments. They are dynamical processes on systems that are eventually quantum. So this was somehow a development which accompanied the ability or the increasing ability with our technologies of coherently manipulate individual quantum systems that encode information. So this ability to manipulate coherently at individual level with increasing precision quantum system led then to the possible implementation of what would be considered or can be considered the prototypes of quantum algorithms. Now, in this framework, however, the main enemy is decoherence, because we do know that quantum information is encoded into quantum systems that are then prepared in typically strongly quantum system and quantum effects like quantum superpositions or entangled states, and these states are extremely fragile, and because of the presence of the connections with the external environment, the environment induces errors or noise, and therefore only if we are able to introduce and develop sufficiently advanced error correction techniques, we will be able to achieve a fault tolerance. And this is something which is still really experimentally at its infancy. While there is a lot of theoretical work being done for fault tolerance in quantum systems, experiments are still lagging behind. Now, I would say that my personal opinion is that it is not yet clear at the moment whether really eventually will be a fundamental limiting factor. It seems most likely that this is just a technical factor, and that as time progresses, we will be able to scale up devices and also at the same time to be able to reduce the level of noise needed to introduce error correction. But there seems to be not let's say, certainty in this direction. So it is still something that people, in terms of universal quantum computer, consider maybe a 10, 20, or 30 years away from now. And therefore, it is considered as really the grand challenge. Will we ever be able to develop such algorithms and therefore to run what are the most famous and most well-known quantum algorithms? While we wait and we continue exploring these directions, at the same time, we can people started and the community started to investigate something that could be considered a shift in perspective, because they started to ask what are actually the useful problems which small quantum computers could solve efficiently. So if we assume that we have not many, say 5, 10 qubits, and that they are noisy, this is the level of current devices, is it possible to identify really the category of problems which could be experimentally obviously less demanding than implementing Shor or Grover search algorithm, but that could somehow be already now advantages on small noisy devices. And one of the, so I have there are three main groups of such problems. The first one is under the name, goes under the theme of quantum simulations. And this is indeed probably the leading original idea of quantum computers, which was initially conceived by Manin and Feynman in 80 and 82. And the original idea was simply related to the fact that simulating quantum systems is hard on classical computer due to the exponential increasing dimension of the Hilbert space where the quantum systems are generally described, or where they live. So for many body quantum systems, it is extremely hard to perform efficient simulation. However, one can naturally use other quantum systems to simulate quantum systems with properties that are less simple to control directly. So it's like performing experiments that simulate other systems. And this can be also done in the framework of small near-term quantum devices, as we will see. So this is one of the applications of noisy near-term quantum devices. The second one is in the line of the optimization problems. And so therefore one could think of what I called here as abandoning the exact. So in a way, think that it is unlikely that quantum computers will be able to solve efficiently worst case instances of, for example, NP-hard problems, like, for example, combinatorial optimization problems. However, it might be possible to build specific for purpose quantum devices and be able to find approximate solutions, or perhaps find such approximate solutions faster. So this is a shift with respect to a shift in thinking, which goes under the name of overall name of optimization problems for NISQ, near-term faulty devices. And then we have a final category that goes under the name of variational quantum algorithms. And variational quantum algorithms are the focus of the remaining of this talk. They have to do with the idea of combining quantum and classical algorithms in a hybrid, creating a hybrid device or a hybrid algorithm in itself. And I will describe better this specific class of algorithms in this talk. So in particular, I will focus on what are known as variational quantum eigensolvers. So this is in the framework of simulations, for example, to simulate the behavior of small molecules or chemical compounds in general, where the problem is of course, to understand. Actually, one of the main questions is to understand what is the ground state, so the minimal energy, for example, of a molecule. And to do this requires, as we will see, an incredible amount of resources, but it is very suitable to be tackled in the framework of variational quantum algorithms. So the idea is to minimize the energy of a many-body correlated quantum systems. And this means that if H is the Hamiltonian of the system, generally this requires the calculation of the mean value of the Hamiltonian, which is basically the energy of the system on a given state. In which way we explore the quantumness of the devices, because we can, sorry, go back. Because, no. Yes, because we can explore the exponentially large Hilbert space of the fermionic particles in order to find, importantly, in an iterative way, the ground state of the Hamiltonian. And so this allows to bypass the more direct approach that would be, of course, to diagonalize the full problem. So the full Hamiltonian of the many-body system, which represents which is actually the molecule in this case, that we want to describe in a fully quantum mechanical manner. So more specifically, this is an example of how an electronic Hamiltonian looks like for example, for a molecule. So we see this expression, which consists of three terms, and which in general describe the kinetic and potential energy of the molecular compound, and that we in general describe in second quantization. So we introduce this second, or we quantize this model to obtain the Hamiltonian in terms, which is expressed here in terms of the creation and annihilation operator of electrons in the single electron spin orbital. So here, for example, these creation and annihilation operators are described by A dagger and A. So this is an exact second quantization Hamiltonian. In general, it's very complex because it contains up to n to the 4 terms, and it contains also these integrals. That take into account, they are related to the original problem, and in particular the HPQ contains the kinetic energy terms of the electron, and therefore their Coulomb interaction with the and their Coulomb interaction with the nucleus, while the second term with the nonlinearity contains the electron-electron Coulomb repulsion. So this is the starting point for variational quantum eigensolvers, okay? And generally, what we want to, the way we want to proceed is we want to find the ground state of this many body system. And as you see in this plot, in particular, what we want to understand is how the ground state energy changes as a function of the interatomic distance, here expressed in angstrom. So we want to reconstruct this curve. This is, for example, for H2 molecule, okay? So we want to reconstruct this curve, and this is useful to understand the chemical reaction and to, in general, for a number of problems related to quantum chemistry. So in particular, finding equilibrium bond length, bond angle, dissociation energy, and therefore it's a quantum chemistry problem. Generally, the reason why this is very difficult to perform will be clear from the very nature of the very quantum nature of the state which characterizes this molecule, when we consider, in particular, in the case of presence of strong correlations. So the problem is that the Hamiltonian that we start from is a fermionic Hamiltonian. So as I say, these are annihilation and creation operators of fermions in given spin orbitals, while we want to map it into a qubit Hamiltonian, because quantum devices operates with qubits, with quantum bits, and therefore we want to obtain or to create this mapping in order to be able to implement this minimization problem and finding the ground state in terms of qubits, so in a qubit system, and potentially with gates, so in the circuit model. Now, in general, this passage is always possible, and there exist different types of mappings from the fermionic problem to the qubit problem. And the qubit Hamiltonian, which is consequent to this mapping, in general will be expressed as linear combinations of K Pauli strings, where the Pauli strings are products of Pauli operators of this form. So and they contain several products of Pauli operators. In general, we indicate with Pauli weight the number of non-identity single qubit Pauli operators in a Pauli string. Generally, these numbers are very high. Now, I will not go into I will go very quickly, so I will not focus on the description of the different fermion to qubit mappings. There are some technical interesting aspects to consider, and some of them are more well known from the condensed matter family, let's say condensed matter physics. Others are let's say, in a way specifically envisaged in order to tackle this problem in the variational quantum eigensolvers framework. But we will go quickly through these. So I will not focus much on this mapping. The only thing that I will say is that generally we will be focusing, I should present 4 of them. For several reasons, we will be using this mapping, which has somehow the advantage of a lower Pauli weight. So I will go quickly to the mappings because they are technical and I don't want to bore you with that. But once you have mapped the original fermionic problem into the corresponding qubit problem, then the first thing that happens is to prepare, in the spirit of variational quantum eigensolvers, is to prepare the state, which will be the ansatz, the initial guess, with the only, let's say, initial guiding idea of thinking of a state which has a sufficiently large overlap with the target eigenstate, the ground state, which in general is unknown, but that you can have, let's say, some sort of guess. So initially it's just an ansatz, okay? There's a lot to say about different ansatz. There is hardware efficiency ansatz, chemical inspired ansatz. I will not go into the details. People are really trying to figure out what is the best way of initializing initializing the whole variational quantum eigensolver procedure and algorithm. But the most important thing is that what you perform is now the generation of a quantum state according to certain parameters that I indicate here with theta that can be manipulated and adjusted. This is generally done by applying certain gates, and in particular, these parameters are encoded into rotations at different angles. So what you do is initially is exploiting really the quantumness of the near-term quantum computer in the phase of the generation of the initial state, which is the initial guess, okay? And then we will keep updating this guess by the measurements. So in this sense, we will have, let's say, a clearly quantum part in the algorithm, which is this one, the initial state generation, and subsequently a more classical part, which has to do with the transformation of the quantum system into a classical string by means of measurements. So after performing this initial state encoding, we measure each of the qubits locally, and this is an example of measurements. And of course, because the Hamiltonian is expressed in terms of Pauli strings, we want to measure each qubit in order to obtain the mean values of all the corresponding Pauli strings. So this is just an example of a measure for a given Pauli string P1, which could be sigma x, sigma z, sigma x, sigma z on for example, 4 qubits in this case. So once we do this, we need to repeat many times to accumulate statistics. And as a consequence of this first stage, we will obtain a mean value of the energy measured in terms of as a result of the measurements, and therefore accumulating sufficient statistics, which then needs to be optimized by means of certain classical techniques, for example, gradient descent. So you want to optimize it in order to go towards the minimal energy. So this is something that is done classically, and this enters the classical section of the algorithm. And then once you change the values of the parameters by using this classical optimization part, you will create again an initial state in terms of the new parameters encoded in the quantum computer, and measure it again, and proceed in this way iteratively until you obtain the state which has the minimum energy. Okay, so this is basically the way in which variational quantum eigensolvers work. And I could say that in general, the impact given by a successful application of this type of techniques might be enormous, because it would allow to solve intractable problems in chemistry. This is very often the case whenever you have strong, or some within the molecules, some parts at least of it exhibit strong correlations. And this can be in turn very useful to understand the model high temperature superconductivity for biochemical reactions, to describe transition metal catalysis, and so on and so forth. And also in general, in material science for the design of new compounds, and for in chemistry and in drug development for drug design, and so on and so forth. So this is the potential impact of such an approach. Now, what is the problem with all this? The problem is that there are major roadblocks in variational quantum eigensolvers. And the roadblocks are twofold, or at least there are two main ones. The first one is the fact that, of course, the optimization procedure can become extremely difficult in practice to solve because of the presence of many local minima and because of a rough configuration landscape. It is not said that you will find the real minimum, but you can be stuck in local minima. And for this, obviously, choosing appropriately the answers and understanding, or sort of complementing with what is known for classical approaches, this is a crucial way to proceed, and there is a lot of research in this direction. But the second, hi, can you hear me? I don't know what happened, but I was
Yes,
kicked out from
yes,
the.
I'm sorry. Something with the Zoom meeting was going on, and I couldn't upgrade for some reason. I don't know why, and now it's upgraded. So I don't know what happened actually.
Okay, okay, but anyway, now it's you still see
Yeah,
me.
we are back. Yes.
Okay, very good. And the second is the measurement problem, which I'm going to explain now in particular. So for many interesting Hamiltonian, as we increase the size of the problem, the number of measurements which are needed to understand, to perform efficiently, or to reach a level of precision like the one needed, is really prohibitive. This is true in particular because even if we would be advantages, the number of measurements will be so large that it may take years to reach, for example, in what in chemistry is known as chemical accuracy. And of course, in this case, this is precisely the framework in which we can introduce an alternative to this problem. So we try to address the measurement problem by introducing some new ideas that can be used in general to improve such a problem in any variational quantum algorithm. So I will apply them again to chemistry, but in principle, they are rather general. And this perspective has to do with the possibility to introducing a method that is based on so-called informationally complete measurements. So let me explain what is the strategy. So in general, for any observable which is expressed in terms of Pauli strings, the main problem related to measurement is related to the fact that the error in the estimation is related to the number of measurements on each Pauli string according to this formula. So this obviously means that the variance of the observable is the sum of the weighted variances of the individual Pauli strings. And even if there exist methods or approaches like the group Pauli method, which aims to identify all the Pauli strings that can be measured simultaneously from the same data sets, even if one tries to use this type of strategies, they are not efficient as we scale with n. So instead, what we propose to do is to replace the standard measurements in the Pauli basis with the so-called informationally complete measurements. In particular, informationally complete positive operated value measures, which are a very important theoretical concept in quantum information theory, and that now we use for the first time in the framework of an adaptive strategy in variational quantum eigensolvers. So this type of measurements are such, the reason why they're called informationally complete is exactly because they are a basis in the space of operators of the system, of the reduced system, and therefore they are allowing not only to estimate the mean value of the energy, but actually to estimate any expectation value. And what we are doing is that we are combining our results. We are using a combination of introduction of informationally complete data with a hybrid quantum classical Monte Carlo that will be used to alleviate the measurement problem. So let me explain how this works. So I will begin by introducing the quantum classical hybrid Monte Carlo algorithm, which can be, again, the key idea can be summarized by saying that so measuring a linear combination of a large number of Pauli strings is reduced as a problem to performing numerically a Monte Carlo integral. And to understand how this works, we can rewrite, recall that we can rewrite any observable, for example, the Hamiltonian, if we want to calculate the energy in terms, which is expressed in terms of the Pauli string, by expanding each of the Pauli operators in terms of the P of M's. If we do this, we can group the terms of the expansion scheme skillfully, and we can notice that these WMs which appear in the expansions are just, they can just be used in terms of probability distribution. So we would calculate the mean value of O just by drawing from the probability distribution the WM. So what does it mean in particular? In particular, what this means is that we can repeat the measurement S times, and we can use the local POVMs to sample from the probability distribution PM. And therefore, we can, because we can calculate the WMs on a classical computer in an efficient way, we will be able to estimate the average of all the Pauli strings simultaneously, regardless of the fact that they commute or regardless of the reconstruction of the density matrix. This is just due to the fact that because we use informationally complete data, we can expand the Pauli strings in terms of the POVMs. This circumvents, on one hand, the cost of tomographic reconstruction because we do not need to reconstruct the full state. And on the other hand, it takes into account the covariance between all the parallel measurements that could exist. And in our case, it is not sensitive. So our approach is not sensitive to this. Now, okay, so this is the first part which uses POVMs. And the second important ingredient is the fact that we can, precisely because we use this type of local effects, we can also go in a direction in which we optimize the POVM used at each iteration. So we will use some classical post-processing routines to navigate in the space of all the possible POVMs in a way that we go at each run, at each cycle, towards those that have lower variance. So in this way, we are moving towards the optimal measure. That's why we say we are learning to measure by exploiting this classical post-processing. And of course, this is something that we can do because we can calculate the variance since we can use the same data because the POVMs are informationally complete. So I can use them not only to calculate the energy, but also to calculate the variance. And this is done, of course, on a classical computer, again, using the gradient descent. So importantly, this can be done on the fly. I do not need first to optimize the POVM and until we reach sufficiently small variance and then start to estimate the expected value of the observable. But on the contrary, we can use the intermediate POVM in the process iteratively, so on the fly. And this strategy is used to calculate a weighted average of the estimated means in a way that minimizes the resulting variance in the estimation. So I will now combine these key ideas to give a summary of how the approach works, okay? So importantly, we use the informationally complete data twice. We use them to produce an estimation of the mean of the observable, for example, of the mean energy, and to find a better POVM in the next experiment. And of course, we can do this precisely because we do not need to have additional measurement costs in the dynamics. So you see here, we generate the state parameterized by theta. We perform the informationally complete POVM, and then we do classical post-processing. In this classical post-processing used both to estimate the mean values of the energy and of the variance, or the observable or its variance, and also within the gradient descent to find a better observable. And then we repeat the cycle. We repeat the cycle with a better observable and see that this improves, of course, the performance of the overall algorithm. I will conclude now by showing some results. And these results are results in which we calculate the estimated and the actual. So estimated is the dashed line and the actual is the solid line error in the estimation of the ground state energy. So this is the error in the estimation of the ground state energy as the function of the number of shots necessary to obtain statistics. And of course, we do this for different molecules, H2 lithium hydride and H2O, with different mappings, fermion to qubit maps. And we see here different curves of different colors. In particular, the blue lines are the typical strategy used, for example, in Qiskit by IBM quantum computer. So this is the line that you can see here. There is a bit of advantage in the grouped Pauli method, but in general, so you can see it better here, for example. Then the use of POVM without optimization is the green line here. And finally, you see that when we use our approach with optimization, the error decreased very fastly until reaching chemical accuracy. That is in general, what is considered the value of error that is useful for performing quantum chemistry calculations. So in all cases, the adaptive strategies is very quickly improving the error, minimizing the error, crossing or showing a behavior which is of course not deviates from the square root of n typical statistic behavior, just because we keep optimizing and changing the POVM on the fly. Okay, I will actually jump on this. The second thing that I want to, second results that I want to mention is the fact that we can obviously study and try to understand what is the scaling of the number of measurements required and the number of shots required to achieve a target error. In this case, again, is chemical accuracy. In this example that I'm considering, we only consider H chains. And here we consider the number of shots required as the number of qubits is increasing. So for increasing number of n, obviously the scaling is what in general counts, because for small number of qubits or for small molecules, for small systems, very often the classical simulations are very accurate. So what you want to do is to exploit the full quantum advantage as the number of qubits and as the complexity of the molecule increases. And again, we have the same coloring. So the blue is for Pauli and for grouped Pauli strategies. The green is for the POVM, for a specific type of informationally complete POVM known as SIC POVM, again in green, and the red is the scaling of our approach, which includes the optimization. And as you see, the scaling is definitely better, as you can see from the dependency of this line. And in particular, we can also derive the exponent of the scaling for different types of fermion to qubit mappings. The best one, as I said, is what is known as the JKMN mapping, and in this case the exponent is 3.4. This is really comparable with what are known to be the best scalings for the best. So the algorithms that provide the best scaling that however are limited in a way to quantum chemistry, so to the calculation of the energy of the molecules, so the ground state energy only. While in this case, and I will explain this in the next slide, we can also from the same, using exactly the same data, not only calculate the energy, but also calculate any other observable that we and therefore solve or study other problems of relevance. And in particular, here, to show what this is possible to do, we use exactly the same data that are used to calculate the mean energy to do partial tomography. So tomography of the 2 qubits, 3 and 4 qubits reduced density operators. And we do this for two different types of molecules, and we see that in both cases the optimal strategy is the use of the gradient POVM, so the adaptive approach, as you can see from the red curve. And this here K, so this is the fidelity of the reconstructed state with respect to K, where K identify again the number of how to say, the dimensionality of the reduced state, whether it is a 2-qubit, a 3-qubit, a 4-qubit, and a 5-qubit state. So concluding, the main message that I wanted to send is that it is possible to overcome the measurement roadblock in variational quantum eigensolvers by introducing a twofold, let's say, new direction. The first one is changing the type of measurements from the standard Pauli measurements to informationally complete measurements, which however require a doubling, so to double the number of qubits requested, as in one of the previous slides. And the second important thing is that we introduce another method to somehow hybridize classical and quantum by providing an approach for iteratively improving the measurement chosen by means of an adaptive strategy. So in this way, we at each round of the iteration, we choose the optimal measurement in order to, for example, minimize the energy. And we think that in this way, we believe that application of this approach to variational quantum algorithms might be opening or paving the way to the use of this type of approaches for near-term quantum devices and to prove quantum advantage in quantum state chemistry. Thanks for listening. That's all.
Thank you very much, Sabrina. It was a very interesting keynote. And I think it was a very innovative way of giving a presentation with this fancy camera and setup. Thank you very much. So now we have time for several questions. So I see that Aikov have one question. So please turn on your mic and probably camera and ask. Go ahead.
I have, okay. In my previous incarnation, I was a physical chemist. So, and I did calculations with small molecules. So I have 3 questions. The first question is, but I don't know if it's relevant at all. Do you use the Born-Oppenheimer approximation?
Yes, it is. It is assumed, yes. Mm-hmm.
Okay. The second question is, there is a giant difference between molecules with 2 atoms or 3 atoms, like H2, LiH, or water, and drug design, and not to speak about biochemical interactions. So, do you have any estimate of what is the gap that
yes, yes, it's a very important and relevant question. Yes, so obviously all these calculations are just proof of principle for which only the scaling seems to be interesting. But obviously at the moment, the devices, the quantum devices that we can use are up to, I think 65 is IBM, the largest IBM quantum device. I think that in order to achieve something that might be meaningful from the point of for real in quantum chemistry, we would need to have of the order of between 300 and 1,000 qubits. So this means that I would say this would, if you look at the roadmap, for example, of IBM Q devices, I think that they plan to have 1,000 qubit within the next year or 2 years. Now I don't remember the exact time, but in principle, this is something that should be available in the next years to come. But of course, there are a number of, at the moment, the devices are still so noisy that it would be difficult really to guess what are the actual, let's say, to make a proper estimate of a use case of real importance, for example, for drug development. It's something which at the moment is the object of study. So this is something we are developing. Personally, we are developing also in my startup. Okay, so but it is by no means something that is easy to identify, precisely because you have to juggle so many variables and so many still unknown factors, among which also the effect of noise and how to describe these algorithms in presence of noise. But not only this. So there are a number of difficulties that need to be overcome before we will be able to prove a useful advantage at the level of useful molecules for example, for even small molecules that are used for drug development. So it's a very good point, yes.
My third question is, I apologize for my ignorance, but can you explain in a few sentences, why do we need to map fermionic sets of particles into qubits? I didn't understand that point.
Yes. Okay. This is, and again, it's absolutely a very good question as well. The reason is that these quantum devices that are, let's say, these small quantum computers that exist nowadays. So the assumption is that we want to use the quantum devices that exist currently for example, there are several companies even offering them online, right? Now, these quantum devices are based on the quantum gate models. So there are circuits that are composed by gates that operate on quantum bits. So this is the hardware which is given to us, okay? So given that we are given an hardware which operates transforming bits, then what we want to do is, in the spirit of Feynman and Manin, what we want to do is that we want to see how we can, first of all, map a fermionic problem, which is the quantum chemistry problem, into a qubit problem, because we want to use the existing device which manipulate qubits. So that's, of course, it's also absolutely interesting. So I have to say it's absolutely interesting also to think in a different way. So there are laboratories in many important and super high-level laboratories where they can also simulate directly fermionic systems without going in the qubit and quantum gates model. This is also possible. It's another type of quantum simulators which are not passing through the qubits and gates model. It's not and it's very valuable, and there are many results also in this field. Yes, very good point.
I understand that your explanation is telling that you need to introduce the anti-symmetry in this.
Yes.
Okay, thanks.
That is the difficulty. I skipped over the mapping, but of course it's very complex. The mappings are very highly non-trivial, precisely because you have to do all the Slater determinants, and you have to be able to take into account, of course, of the fermionic nature of the initial state of the system. But yes.
Yes, so we have time for several other questions. We have about 10 minutes, 9-10 minutes. So if anyone has any question, we take them first. Yes?
Yes, I would have a short question, please. I know for the machine learning approach that quantum computers are often used to solve some subtasks of machine learning approaches. Is there something similar available where quantum computer maybe performs a subtask of Hartree-Fock or something like that? Or is it not common?
Yeah, it's a good question. I think that this might be possible. I do not know really. Well, I cannot give any specific example, but I think that in principle it might be possible. Of course, there is at the moment a lot of research in the field trying to exploit. The key, what I can say is that the key ingredient here would be in a way to exploit the fact that you can encode, you can take into account, really, you can really, how to say, so the state of the multi-qubit is able to represent really effectively the state of many electron or a complex molecule, of the different electron spin orbitals in the molecule. So it is naturally so, because you can have all the possible superpositions of states naturally encoded in the many qubit state. So the whole point is you use it in a minimal sense, because you see, I'm not performing in the variational quantum algorithm that I presented before, I'm not performing any gate or any unitary to evolve, for example, the system. I'm only performing gates to generate the state. So in a way, is the only thing that is quantum is the generation of the state, which then is modified in order to reach the ground state. But it's only the encoding of the information necessary to characterize a quantum many-body state. This is the only part which is quantum. So anytime you want to use this to your advantage, then it's worth using this type of approaches. But that's like the minimal quantum requirement. I'm not using any dynamics. There is no time evolution here of the system. It's just the encoding of the state by using the fact that I do have a quantum system, which allows me to generate any superposition of a many-body state or entangled many-body state. Indeed, in a way, the point, so where it will become useful is anytime you will need, for the original problem, the description of strongly correlated systems. So whenever the state that I want to, for example, the ground state of the system that I want to generate contains strong correlations and therefore is necessarily described in terms of quantum systems, then I would have an advantage in doing that, because strongly correlated or strongly entangled systems are not efficiently, cannot be, in the case of many-body, so for increasing number of qubits or n, they're not, we can't store them, we can't analyze them, we can't prepare them, or we can't keep track of them classically, just because we run out of memory.
Okay, thank you.
Thanks.
Yes, if anyone else from the audience. Rui, is it also possible to see in YouTube, or probably
Yes.
not yet?
Let me check.
If there is someone question.
No questions there.
Okay, so maybe we have few more minutes. So maybe since our community, this workshop is about quantum software engineering. And I was just wondering that based on your experience in working quantum algorithms, how do you view this area of, it's a very high level question, not specific to your keynote, but how do you view how do you view quantum software engineering, and where do you see it going in few years? Do you think it's a good area to work on, or what's your opinion? I mean, in general.
Thanks, of course. Thank you very much. So yes, so well, obviously, one should consider that in order really for the quantum computing and quantum technologies in general to become fully developed, in order to speed up the process of the, what we call the birth or the rise of the quantum ecosystem, we will need to act at different levels. Okay, so the level I've been discussing here is really very much still physics level. Okay, even when I talk about these algorithms, I use a lot of physics. Okay, there is a lot of physics. It's not very high level, software language. Okay, it is really I'm almost talking about these algorithms in terms of physical experiments. Okay, I talk about measuring the expectation value of an observable and these other things. And this is generally because this is the way in which nowadays, if we think in terms of programming these devices like the IBM quantum computers or the Google quantum computers, they are programmed still in order to obtain something which is new and meaningful. You really need to know a lot of physics behind. Okay. But of course, at the same time, we need in parallel to think of developing software which is of a much higher level, obviously, than this one, because this is not something that will be sustainable or scalable in the long run. We cannot have experts in quantum physics, to run quantum computers in general. We will need that everyone will have to be able to run quantum computers. In particular, we will need the software engineers that will be able to run quantum computers or to create programs of quantum computers without being quantum experts. Okay, this is clearly a direction that will have to happen, and therefore it is highly valuable that at the level of the higher level, really, of software and of programming, a similar progress occurs, okay? Because as the technology evolves and as we will start to have more and more, advances in the direction of fault tolerance, in the direction of reduction of errors, in the directions of longer coherent times, well, we will be needing, obviously, to think of a myriad of problems related to that actually can be even inspired by software engineering in the classical or conventional computers. And especially we will be needing to think of really how that conventional software will talk to the quantum software. So what will be the interface between these two? Because this is also another. So what I mean here is that it is highly valuable, highly important, and I think it should be definitely pursued because the technology is advancing quickly. So I think the two things are obviously not, let's say, they are not excluding each other. On the opposite, they are complementing each other, and the progress in both are definitely is definitely needed at this stage. I can also add to this that while I'm sure that the language I've been using for describing these results might be not much familiar to many of you with different background, and the other way around, okay, in my case I would be having difficulty. It is obviously crucial and important to try to make an effort also to communicate between these different communities, which is also one of the reasons why I appreciate this type of more interdisciplinary and interfield somehow connections, acknowledging obviously the difficulty in the use of languages and backgrounds which are different. So, but nonetheless, one makes an effort to somehow communicate at least some ideas and some directions.
Thank you very much, Sabrina. So let's see if we have time for one more question, but it doesn't seem like we have any question. But with this, we'd like to thank you very much for giving us this very interesting keynote. And I think it gives us a very good perspective on.
There is another question, I think, from Matteo.
Okay. Yes, please ask.
Okay, thank you. Can you hear me?
Yes.
Yes.
Okay.
Yes.
Yeah, thanks for the talk once again. So from what I understood, so I'm quite new to quantum computing world, but I understood that there are like different kinds of way to implement a quantum computer. So there is the way IBM is doing, and there is also another way that is the one pursued by D-Wave, another company. I wanted to know if you make the assumption to use this, you decided to use the IBM quantum model, so the circuit and gate model, for a specific reason, and if there are also, if it's theoretically possible to solve the same kind of problems that you're trying to address by mapping to another kind of architecture, for example, like the one of D-Wave, and if there is any kind of like line of work that's trying to do the same. Yeah. Okay. Thank you.
Thanks. This is a very good question. Of course, what D-Wave is based on annealing. Really is the way in which D-Wave's quantum computers work and what they exploit. They are actually specifically aimed. So I wouldn't call them in a way some, let's say, universal quantum computer. They are some simulator and they are optimizers machines. So they are aimed at optimization of specific problems. So they are naturally, let's say, more focused on a specific purpose, of course, of a great variety, because optimization, there are a lot of optimization problems that can be solved on D-Wave machines, so for sure. While the IBM quantum computers based on the circuit-based model, in principle, can be, in the future, can lead, provided that one reaches fault tolerance, can lead to universal quantum computer machines. So they're not just a specific purpose in a way, in general, okay? They are now in what we cannot solve not many things, but in principle, the circuit model is a universal model, which we can use to universal. Now, when it comes to variational quantum algorithms, I'm not aware of variational quantum algorithms for annealers or for D-Wave machines. So as far as I know, I haven't seen in the literature this devices, but it's an interesting question. I think they do operate differently. Yes, very much. Yes.
Thank you.
And annealers obviously are not so much based on quantum gates, but.
All right. And with this, we would like to again thank you, Sabrina, for a great talk and giving us a new perspective on quantum computing. And thank you very much. So
thank you.
Thank you.
Thanks.
Bye-bye.
Bye-bye.
So for the next session, Rui will be the chair. So do we have speakers for all the talks, or shall we also get ready the video?
I have just made Yakov and Alon co-hosts, so they are the authors of the first paper. Are the authors of the second paper also here in the session?
I think they sent me an email that they will. So I think I can try their video. So we have so.
Okay, and then for the third paper we have Felix here. I see him.
Oh, I see.
So I can also make him co-host. Here you go.
So shall I maybe since video can be trouble, so maybe can I quickly try it?
Yes, we have like a minute.
Yeah.
Yeah.
Can you hear me?
Yes, not the video though.
Okay. So is it not working, right?
No video. We could see the image, but not the video. Not the sound, sorry. The video was okay.
Check this. Still not.
No. No.
Okay, I think then meanwhile we start the session, I can try to switch it to the second one. Yep.
Okay, so let's get started with the first session. This first session is on modeling, and we have 3 papers. The first one is by Jakov Eksman and Alon Shmilovic on quantum software models. Jakov, Alon, can you share your screen, please? And unmute yourselves. Okay, Jakov has just done it. All right, you may start, Jakov.
1 second. And here we are. I'm going to present our paper accepted for this workshop entitled Quantum Software Models, the Density Matrix for Classical and Quantum Software Systems Design, by myself, Jakov Eksman, and my co-author, Alon Shmilovic. We have 2 messages. The first message is that there should be a single rigorous design procedure for both classical and quantum software and not separate procedures. The second message is the common starting point is the von Neumann's density matrix. Our agenda for this talk is to start with an introduction to the Laplacian matrix. Then the theory in terms of density matrix software modules and theorems and procedure, followed by case studies illustrating the theory, a classical one and a quantum one, and concluding with a discussion. We have used Laplacian matrix for classical software systems, and the classical software system is represented by a bipartite graph, which has 2 kinds of entities, structures S1 to S4 in this example, functionals F1 to F4. The structures describe the structure of the system, and functionals describe the functionality of the system. You can see here in this sample examples 3 modules on top of the blue background. The Laplacian matrix is defined by D minus A, where D is the degree matrix, which is a diagonal matrix on pink background, and adjacency matrix telling which are the neighbors for each of the vertices. For instance, the vertex S3 has the neighbor F3. How to get modules from the Laplacian? One calculates eigenvalues and eigenvectors, and the modules are obtained by the eigenvectors corresponding to eigenvalues which have a 0 value. In this case, there are 3 eigenvectors. The first one is with 1 value vector element in F1, F2, S1, and S2. These are the labels of this module, and it corresponds to the modules that we have seen in the previous slide. And there are 2 additional eigenvectors, one with F3 and S3 labels, and the other, the final one, with F4 and S4 labels. Now, we move to the density matrix because we will wish to be able to deal with quantum software models as well. The density matrix rho is a matrix representation of a density operator, which is a projector, or in Dirac notation, it is a ket bra. So rho equals ket of psi, bra of psi, where psi is a generic notation for a quantum state. The density matrix rho is easily obtainable from the Laplacian L of G by scaling the Laplacian by the sum of the degrees of the graph G. This was observed by Brownstein and co-authors. This gives a novel perspective on software modules. In the previous case, the modules were the connected components. In this new perspective, we shall see that a module is a partition of the projectors of the cats in the system basis set. So let us look at the previous matrix. It has an 8 by 8 matrix, the Laplacian, so dividing by the sum of the degrees doesn't change the number of columns and rows. So we have the basis set has 8 cats from 0, 0, 0, 0, 0, 1 until 1, 1, 1. And the projectors are obtained by from the density matrix using the cats, the projection from the cats in the basis set. So the definition that we are using here is that a module of a software system is a subsystem of the given software system, which spans a subspace of the space of the whole software system, given by the partition of the projectors. So we have two theorems. The first theorem, what is the number of software modules? The number of software modules is the number of the partition classes of the basis CAD projectors. Which are the components of the software modules, which means what are the structures and functionals. They are the structures and functionals fitting the projectors of the given partition class. So, summarizing the procedure to obtain modules from a density matrix to modules, we first apply the density matrix to each cat in the basis set, obtain the projectors, and express the density matrix as a projector's sum. Then partition the projectors into disjoint projector sets and getting the number of modules by the number of disjoint projector sets, and the components by the basis cats of the respective projectors, which are in a one-to-one correspondence with the with the labels, the structures and functionals. Example, we give two examples, one classical and one quantum, to show that the same approach can be applied in classical software systems and to quantum software systems. The classical case study is a prototype design pattern, which is a well-known design pattern in the Gang of Four book, for those who are familiar with the design patterns book. And from the class diagram of the design pattern, we obtain a list of structures and a list of functionals. The list of structures is, in the class diagram, the structures are classes and the functionals are methods. So The first structure is a generic clonable shape. The idea here is that we can replicate shapes as needed. So one needs to be able to clone shapes. The second structure is definition of specific shapes, such as triangle, square, circle, etc. The shapes cache serves to store those shapes that we have already cloned. And we can retrieve from the cache a desirable shape. If the shape is not yet stored in the cache, one uses a clone function, which is inherited from this generic clonable shape structure, and generate that shape, store it, and use it as needed. The prototype client is the structure containing the main function which triggers the whole process. We have already explained the meaning of the functional, so we can look at the density matrix. The density matrix is the Laplacian, not by chance the Laplacian that we have seen before. And we have to scale the Laplacian by the sum of the above the sum of the degrees of the vertices. So here the sum is 10, so 1 over 10 is 0.1. And the second point that we wish to emphasize here is that please do not confuse the labels of the different columns, F1, F2, and so on until S4, and the labels of the rows, F1, F2, and so on until S4, with the cats above the columns and to the left side of the rows. The cats are and the bras are the basis set, and we in order to get, for instance, the column S2, we apply the density matrix on the cat 101 and obtain that column. And that column has some coefficients, -1, -1, 2, that can be expressed in terms of the other columns in the matrix. Now we get the modules by the procedure that we described earlier. For each of the cats in the basis set, we obtain projectors, and we separate all the projectors into disjoint sets. And here we have 3 disjoint sets, one over the yellow background, one on the orange background, and the third one on green background. And the corresponding labels F1, F2, S1, S2 can be easily obtained from the columns of the density matrix. So we have here 3 modules, and how to validate this result by simply comparing this quantum software model with the linear software models in slide 5, which were obtained from the eigenvectors and eigenvalues. The quantum case study is the well-known Grover search algorithm. In the classical case, we obtain the structures and functionals from the class diagram. In the quantum soft system, we obtain the structures and functionals from the high-level quantum circuit that can be seen here. We see 4 boxes. The first box is the initialization, which contains the Hadamard gate to the power of tensor n. And this gate just puts the input into an equal superposition state. The next box is an oracle, which recognizes and marks a target. The third box is the target amplification, which is obtained by an inversion about the average. The expression here, 2 times the operator, the Cat-Brown psi minus I, is exactly the function used by this amplification. And finally, one performs a measure after the desired target that was recognized and marked, and the amplitude is amplified enough so that it is obviously the only result, or to a high probability, the only result of a measurement. Then we get the searched item. We want to point out that these 2 boxes, the oracle and the amplification one, consist together the Grover iteration. The initialization is performed just once. The measurement at the end performed just once. But the Grover iteration is performed in a few cycles of the order of square root of n, the number of searched items. So we look at these 2 boxes as a single module. Here are the lists of structures and functionals for this case, obtained from the quantum circuit. The boxes we have seen in a minute ago: the initialization, oracle, amplification, and measurement. The Grover iteration is on top of the blue background. The functionals we have already seen. They are equal superposition in the initialization, oracle to mark the target, amplification to make inversion about the average, and measurement to obtain the result of what is being measured. The justification of looking at the oracle and amplification as a single module is it is twice can explain. The first one is because this is a cycle which is repeated again and again until we have amplified enough the desired target. And second, in analogy to the classical software engineering, these 2 structures have functionals which are exactly the same function. The oracle is I minus 2 times the projector of omega. Omega is the market target, and the amplification is 2 times the projector of psi minus I, which they are exactly the same function with a different argument, and multiplied by -1 because we have an inversion about the average. No, sorry. Okay. The density matrix of the Grover search algorithm is very similar to the density matrix of the prototype design pattern. And the only difference, significant difference, is that the 2x2 module here is in the middle, in between the upper module and the lower module. And in the case of prototype design pattern, the 2x2 module was in the upper position. Now, we ask, do we expect to have so similar density matrices? The answer is no. There is no reason to expect the same or similar density matrix between so different algorithms or software systems, such as the Grover search algorithm and the prototype design pattern. So it is by chance, but it is telling us something else which is useful, that the dealing with quantum software systems and with classical software systems is not so different. It is probably a good reason to do that. Discussion. First point is that different density matrices of a software system may be used for distinct purposes and may be obtained from different basis sets. The second point is that we prefer to start the description of the analysis of software design from quantum system quantity, like the density matrix. Perhaps this is not exactly the most intuitive way of doing that, but the idea is that we should look at classical software systems as classical limits of quantum systems, which is an idea acceptable in physics. The third point is the wide density matrix. We look here at the fact that the density matrix is both characterization of a quantum system state and an operator applicable to states. The same is true for software systems, that the readable code is a description of a state, and the runnable code after compilation or interpretation is runnable upon states which are input to that code. We conclude by repeating the two messages. First, a single rigorous design procedure for classical and quantum software systems, not two different procedures. Classical and quantum software systems are the same creature, the same animal, if you wish. And this common starting point, which is linear algebra par excellence, is von Neumann's density matrix. Thank you for your attention, and we are willing to receive questions.
Thank you. So thank you, Jakov. Alon, feel free also to answer any questions that you may have. So are there any questions to Jakov and Alon? Let me see the chat. Well, I can get us started. So one question I have is, how difficult would it be for someone to come up with a density matrix?
The way is a very simple one. If you are working with a classical system, start from, you must have some class diagram. Once you have, we are thinking object-oriented. So if you have a class diagram, then you have classes, you have methods. So you can obtain the list of structures and functionals and possible relations. For instance, inheritance. The inheritance means that two different structures provide the same functional. Once you have the list of structures and functionals, you draw the bipartite graph, get the Laplacian matrix, and trivially divide by the degrees, and there you are. If you are in a quantum software system, then you start from the high-level quantum circuit. This is a good question because classical class diagram is describing only a structure, no behavior. And the quantum circuit diagram is a combination of structure and a sequence, which is sort of behavior. So there are differences. The sources for these differences are the historical reasons. Maybe that we should push both classical and quantum software systems to use this same initial diagrams and so on. The continuation from the diagram is, as you have seen, very similar to the classical case. One more observation is that there is no unique density matrix for each system. It depends on even in terms of software design, it depends on what do you want to optimize. For instance, in the for the Grover algorithm, you can find papers in the literature which that wish to optimize the oracle and the amplification in separate. You must translate the oracle into a set of gates, and the amplification is another set of gates. And sometimes you prefer to optimize the oracle in separate. Then the 2x2 module is not there, even if it is a cyclic operation. Then you have, instead of 1x1 module, a 2x2 module, and another 1x1 module, you have a strictly diagonal representation. You must understand what is the purpose of your design.
Right. Right. Okay. Is there any other question?
Okay. So,
if not, thank you, Jakov. Oh, there is one question.
Okay. Yes. So I just a very simple question.
Oh yes.
So I'm JJ. Yeah.
Go ahead. Yes.
So thanks. Thank you very much for an interesting talk. So my question is that I would like to clarify that. So for example, for your proposed approach for modeling a quantum software system based on for example, using the density matrix. So I just wondering. So is it the first time to propose such kind of approach for modeling the classical and quantum software system, or there is some approaches based on the density matrix for modeling classical software system? I just want to clarify.
The classical software systems, the usage of the Laplacian matrix is found in several places, but what we have done is to be very systematic and to declare that this is the way to do it. Concerning the quantum software systems, we are not aware of usage of the density matrix. What we do know is that Brownstein and co-authors and others studied graphs as graphs. They did not declare that their graphs are software systems at all. So we are not aware that someone proposed this previously.
Okay, yeah, thank you very much. Very interesting, yeah.
All right, thank you. So we'll move to the second paper. The authors cannot be here with us today, so we are going to play. Well, Shaukat is going to play the video. It's from Perez Castillo, Jimenez Navajas, and Piatini on modeling quantum circuits with UML. Go ahead, Shaukat.
Okay. Good afternoon. First of all, I want to thank all of you for assisting to this presentation. I will talk about modeling quantum circuits with UML. And my name is Luis Jimenez Navajas, and I belong to both the quantum team and the LARCOS research group from the University of Castilla-La Mancha. A quantum is a research, development, consulting, and services group in the fields of quantum software engineering and programming, co-formed by Alhambra and Grupo LARCOS. As we all know, almost every day there are relevant news about quantum computing in different and important newspapers or web pages. Like Bloomberg or the Business Insiders, we can see in this slide. China with ambitious goals in 5-year plan, how quantum computing could transform the future, and Israel allocating $60 million to build the first quantum computers. We can conclude that there is a huge expectation of this new paradigm and a high investment for taking advantage of it. So, in the future, the different companies will implement in one way or another quantum algorithms in their systems for taking advantage of its computational power. However, the organizations cannot make a transition toward quantum computing discarding their actual systems. This is because of the classical system are still useful for the companies as they may empt mission-critical knowledge. Also, quantum failed operations won't make sense as the computational gain acquired will be low compared to the cost that the implementation requires. Our predictions about how the different organizations will take advantage of this paradigm will be through hybrid systems, where the companies will migrate some of their mission-critical functionalities to quantum software, while other new functionalities are still implemented in the classical software. This approach will transform the classical information systems into hybrid information systems. The development of quantum or hybrid information systems cannot simply consist of a collection of code modules, but it should rather follow a whole life cycle. It does not matter how long the life cycle is, since what is certain is that the quantum software must be designed at some point. Software design defines the architecture, system elements, interfaces, and other characteristics of the system in order to accomplish goals, using a set of primitive components, and it's subject to constraints. UML can help by gathering, analyzing software requirements and incorporating them into a programming design in a technology and methodology-independent manner. This will make it possible to additionally use UML with hybrid information systems. Although other modeling languages can be used to design software, we believe that the usage of UML in quantum software engineering will have several advantages. First, the different perspective, as UML provides many different diagrams or models to look at the system from various perspectives and concerns. Then the design validation, the aforementioned perspectives allow UML to help quantum software engineers to communicate, explore potential design, and validate the architectural design of the software. The best practices UML represents a collection of the best engineering practices that have been proved successful in the modeling of large complex systems. These practices could consequently be applied in the quantum hybrid information systems. Structure design as UML modeling makes it easier to structure software as a collection of self-contained modules or components. This enables the reuse of code, scalability, and robustness. The tooling, since UML is a widely adopted ISO-IEC standard, most of the design and modeling tools support it. One of the primary goals of the UML is to advance the state of industry by enabling object visual modeling tools. The software modernization UML is not only used for design target hybrid information systems that then will be implemented by forward engineering. UML models can also be generated by reverse engineering tools that analyze existing software, for example, in order to migrate or modernize software toward hybrid information systems. Despite the advantages mentioned, UML needs to be adopted in order to capture all the new semantics and building blocks involved in quantum software. As it was defined on the basis of the metal-object fatality, which is a metamodel, UML is therefore a metamodel that is used to define different UML models, and its extension consequently consists of extending the metamodel. It is possible to extend it by principally following three different approaches. First, a new instance of the meta-object facility model. This approach consists of creating a completely new metamodel based on the meta-model fatality. The result of this heavyweight approach is a new domain-specific modeling language. Second, the derivation of a new UML metamodel. This approach adds a new metamodel element to the existing one. As occurs with the first approach, it is a different metamodel, but at least consider the original UML model as it is. And the last one, the UML profile. This is a lightweight extension approach that it is based on the UML built-in extension mechanism, which is the UML profiling. UML profiles are created as a set of stereotypes, tags, values, and constraints defined for some of the existing UML elements. These three approaches have various pros and cons. The expressiveness of the two first approaches is powerful, since conformity with UML is not necessary, particularly in the case of the first approach. Despite the fact that the expressiveness of UML profile is limited, standardization and conformance are better, since the extension is fully compliant with UML. This advantage is a key aspect as regards the usage of the defined profile with existing UML modeling tools. Moreover, it is easier to maintain extensions that have been defined as UML profiles, since the associated modeling tools do not need to be adjusted after each change, as occurs with the domain-specific modeling tools. And in fact, they usually end up with an overloaded and imprecise language. The aforementioned advantages led us to believe that the UML profile is the best way in which to define the UML extension for quantum information systems. This is the preliminary UML profile design in order to represent the quantum programs as activity diagrams by using a graphical notation like the employed by quantum circuits. It should be noted that a broader UML profile will be defined for the representation of not only quantum circuits, but also the analysis and design concerns of hybrid information systems. The UML profile consists of 6 stereotypes with which to add the new semantic related to quantum circuits. The quantum circuits, qubit, quantum gate, control qubit, measure, and reset. The left-hand side shows an step of the UML metamodel employed to represent UML activity diagrams. The intuitive idea behind representing quantum circuits with UML activity diagrams is that each algorithm is represented with a single compound activity with stereotyped quantum circuits. The entire circuit is, therefore, defined in this activity, and the compound activity can be reused in other circuits, as occurs in quantum programming. The various activity partitions, graphically represented as horizontal swim lanes, can be defined in the parent activity by employing the qubit stereotype. The circuit has as many activity partitions as different qubits used in algorithms. All the different quantum gates applied in the circuits are, therefore, represented as action elements and are placed in their respective swim lane, according to the qubit under which the gate is applied or controlled. On the one hand, ordinary quantum gates, such as Hadamard or Pauli, are represented as CAL operation action plus the quantum gate stereotype. On the other, conditional gates are represented with multiple action elements. The controlled qubits are represented with sensible action elements with stereotype control qubits, while the gate applied is represented with a counter element, accept element, action plus the quantum gate stereotype. Additionally, in order to add the semantic concerning the relationship between the control qubits, various constraints elements are established between the action elements involved. In order to illustrate how the quantum UML profile is applied and to demonstrate its applicability, I will provide a running example by using the teleportation algorithm. This algorithm supports quantum teleportation, a technique used to transfer quantum information from source to destination by employing entangled states. In this example, Q0 is the qubit that represents the message to be sent. Q1 is an auxiliary qubit, and Q2 is the target qubit that will receive the information coded in Q0. In this example, Q0 is not initialized to make the sample more trivial. After the application of the quantum UML profile, the activity diagram will look like this. The whole circuit is enclosed in a composed activity with the respective stereotype. Therefore, has three horizontal activity partitions, one for each qubit. The quantum gates and measure are then placed as action elements in the same position as in the original quantum circuit. One interesting aspect of the quantum circuit represented with UML is that the measures can be connected with data stores node that represent classical values after a qubit is measured. Other ordinary UML elements outside the whole circuit could be connected with elements of the quantum circuits in order to define relationships with classical elements. In this slide, we can see clearly how each of the elements of the teleportation algorithm are represented in the activity diagram. With regard to the quantum gates C0 and CZ, these are modeled with pairs of send signal action and accept event action connected by a restriction edge, together with the stereotypes control qubit and quantum gate, while the Hadamard gate is represented as an action element. The execution flow of the circuit in UML is explicitly represented through the use of control flow elements from the initial node to the activity final node through all the quantum gates. This explicit flow constructs with the original quantum circuits, in which the execution flow is implicit, which has some advantages in some cases, such as the optimization of the quantum algorithms, during which the specific order of the quantum gates may be of interest. Although several quantum circuit notation with which to graphically represent quantum algorithms already exist, the UML adds a similar notation that is understood by the main role players in the quantum software engineering field, and which is available in many existing modeling tools. In fact, the approach followed in this research consists of a lightweight extension based on a UML profile, the built-in extension mechanism provided by UML. Unlike other heavyweight extension mechanisms, we believe the quantum UML profile has two clear advantages. First, the reuse of existing UML modeling tools and the integration with other standard UML elements, which is useful as regards representing hybrid information systems. The example shown previously demonstrated the potential for employing the quantum UML profile in the designing of hybrid information systems, and also it could make more unstable the development of quantum algorithms, helping as a basis for future developments. This presentation proposes the UML extension as part of more extensive long-term research devoted to providing a quantum UML profile that will cover other viewpoints and aspects of the analysis and design of hybrid information systems. For example, use case, class, sequence, component, and deployment diagrams will be extended with the quantum UML profile, and our future research line will compromise precisely this. As future works, the implementation of more complex algorithms like the quantum Fourier or quantum Fourier transformation or phase estimation will be made in order to check the applicability of the UML activity diagrams for that purpose. That was all, and if you have any question, you can start making them.
All right. So, as I said in the chat, so we don't have the authors here with us. So my recommendation is that if you have any questions, just to get in touch with them. In any case, so we'll go to the third paper, and we have two of the three authors here with us, Felix and Antonio. Which of Felix, is it you or Antonio is going to share the slides?
I will share them. Just a second. Can you see the presentation?
So this paper is, yeah, we can see it. Okay, you can go ahead and talk about it.
Okay. Thank you. Hello, everyone, and welcome to the presentation about this position paper titled Towards Model-Driven Quantum Software Engineering. My name is Antonio Garmendia, and I'm the co-author of this paper, together with Felix Gemeinhardt and Manuel Wimmer from Johannes Kepler University, Linz. So the agenda of this presentation will follow this structure. I will start with the introduction and background of model-driven engineering. After that, my colleague Felix will continue with this presentation, giving some introduction about the MDE application from quantum computing, the demonstration case with the initial results and the lesson learned, and lastly, a research roadmap and further steps concerning future challenges regarding the application of the MDE to quantum computing. So nowadays, we face an increased use of quantum computing. Therefore, there exists a vast amount of quantum computing framework, programming languages, and platforms. So developers that use this technology needs to create a real-world application, which usually turns out to be very complex in the sense that they should manage, for example, a lot of qubits. So the application of model-driven engineering may give us, as a result, an abstraction using higher-level languages. In this sense, we can apply the lesson learned from the evolution of classical programming, in which there was a development process until reaching an appropriate abstraction level, such as offered by current object-oriented languages, in order to efficiently develop the software system. So it is reasonable to assume that quantum computing must go through a similar process. Then, what do we expect from model-driven engineering and quantum computing? So basically, the efficiency should increase, in the sense that we must accomplish this by writing more concise code, try to involve the domain expert in the development process, and try to reduce the effort by using a code generation approach. MDE is a methodology that advocates for the use of models in all phases of software development. So this methodology is based on two principles. The first one is the abstraction, in which is frequently the creation of domain-specific modeling languages. And the second one is the automation, in which the code is generated from a model. So in this example, we have our DSML is for creating graph representations. And from this representation, we can generate NetworkX code, for example. And NetworkX is a Python language for the creation and manipulation and the study of complex networks. How we can implement these DSMLs. The DSMLs are compact languages that offer high-level primitives that usually correspond with the specific concept of the domain. To create a DSML, the developers must create an abstract syntax, concrete syntax, and the semantics. Usually, the abstract syntax is described using the meta models that conforms to MOF, the Meta Object Facility. And its concepts are very close to a UML class diagram. So in these examples, we have a meta model that represents a social network, and therefore a social network contains persons and the relationship between them. To create models that conforms to this meta model, we can create a suitable modeling environment. So we can have, in this case, a graph editor with the palette, so to create a specific person and its relations. So from now on, my colleague Philip will continue with this presentation. Thanks.
Thank you. So I will continue now with a short background on quantum computing, and especially from the software engineering point of view. And in this regard, I want to emphasize 2 points. So the first point is there a vast amount of quantum computing approaches out there. So when we look at the quantum computing frameworks, there are different assembler languages, different vendor-specific programming languages, more advanced full-stack libraries and development kits like Qiskit from IBM, the D-Wave Leap, Zerg from Google, Quantum Development Kit from Microsoft, and so on. Then there are the hardware and vendor agnostic universal languages, like, for example, the Extreme Accelerator. There are domain-specific tools like Quasimodo, OpenFermion for quantum chemistry problems, PennyLane for quantum machine learning, or Tequila for variational quantum algorithms. And there are also hybrid orchestration tools for the orchestration of quantum and classical elements. Then when we look more at the fault tolerance side, we have several quantum primitives. So these can be regarded kind of the building blocks of more sophisticated quantum algorithms. So we have, for example, amplitude amplification, quantum Fourier transform, or phase estimation. And then we have the quantum algorithms themselves, like prominent ones, Grover, Shor, HHL, or the whole class of variational quantum algorithms. So with the VQ, QAA, it's the most prominent ones. So that's the first thing that I wanted to mention, that especially the software landscape is quite heterogeneous and there is no unified approach yet. And the second point is the current era that we are in, so the NISQ era, noisy intermediate scale quantum. And in this era, the real-world problems are usually not solved, cannot be solved by a quantum computer alone because they're too big. And this calls for the use of hybrid applications, so the interplay between classical and quantum computation parts. So what we do refer to as a hybrid application, so first of all, the variational quantum algorithms, as they are hybrid in nature, but also in a more general manner, every classical framework that utilizes a quantum machine for some subroutine, for example, solving a subproblem, is to refer to as a hybrid application. So what are now the application possibilities of model-driven engineering to quantum computing? We've already talked about the necessity of hybrid applications, and we have talked about the meet-object facility on the meta-meta model level of model-driven engineering. So the question is now how to fill this gap via appropriate models and modeling languages. Within MDE, models are either created via general purpose modeling languages like UML, or with domain-specific modeling languages, which are specialized to a certain application domain. And these DSMLs can be further categorized into languages focusing on the problem domain, like the one we propose in our paper, or languages focusing on the solution domain. An example for this would be a DSML that serves to ease the design of particular quantum algorithms. And the construction of such DSML starts usually with the definition of the meta model in order to capture all the domain-specific relevant concepts and their properties. And as we said, the definition of this meta model has to happen in accordance with the regulations of the meta-object facility at the meta-meta model level. And when we look one level below, we have the models as the concrete instances of the meta models. And based on such models, one can then create hybrid quantum classical applications. And the reasons why we have also added the quantum ML and quantum models in this figure is that currently we do not know whether the existing modeling languages are sufficient to account for quantum computing, whether they have to be extended, or whether completely new modeling languages would have to be developed because these languages would require the ability to cope with quantum as well as hybrid elements. But that's actually the goal of this paper, to explore this subject for the case of problem-oriented DSMLs. And this is also where our work differs from related work, which, at least to our knowledge, focuses more on the solution domain and therefore examines, for example, how to model quantum elements and quantum algorithms in general without taking into account a specific context or problem, like, for example, optimization or finance or chemistry. So we have created a small demonstration case, which shall really just serve as a first insight on what would be necessary to port the existing DSMLs to quantum computing. And for this purpose, we've chosen the domain, or the problem domain of social network analysis, or community detection in such networks more specifically. So when we look at the graph on the right side, each node represents a person of the social network. Each edge represents a relationship between two people. And the goal is now to find an assignment for each person to a community in such a way that the connectivity between the communities is minimized and the connectivity within single communities is maximized. So conceptually, it's about finding the social groups in a network. For this purpose, several metrics have been defined, and one popular one is the so-called modularity. And when one uses this metric as the optimization function, as we did, we obtain the formula that you can see on the left. And when we look at it, one can see that it's already stated in a so-called QUBO form, which stands for quadratic unconstrained binary optimization. And that's actually the most prominent problem class for quantum combinatorial optimization. So we've seen the problem is already stated in QUBO form, which is good. However, we still face the problem that the graph instance, the problem instance, is too big to be solved or to fit on a quantum device. And therefore, we need hybrid applications. And the question is now how to solve this problem via means of model-driven engineering. As we said, the first step in creating a DSML is to model the problem domain. So we have a social network with several people, relationships, and clusters or communities. Then the second step is to account for the solution space, solution domain. Here we have several quantum algorithms that can be used for this problem. They are contained in a quantum library, and they may be specified by one or several parameters. And the remaining part in the middle serves now to link the problem space and the solution space. So it's actually a Weaver model because it links to meta models with the algorithm execution class in the middle as the main part. And by using this representation, we can now deploy the algorithms with different quantum computing technologies and offer different deployment solutions. So in this sense, first the according models as the instances of the meta models are created, and then the code is generated to actually create the hybrid applications and execute the algorithms for the particular problem. So to demonstrate the feasibility of our approach, we have applied it to the Zaharie-Karateglu graph. That's a rather small but prominent benchmark graph in social network analysis, consists of 34 people. So in our case, the problem instance was the 34 times 34 binary symmetric adjacency matrix of this network. And on the solution side, we have utilized 3 hybrid quantum classical algorithms. The QA1, which was based on quantum annealing, then the GB1 and the GB2. The GB1 and GB2 are based on gate-based approaches, and the GB1 just iteratively finds the strongest community in a graph. Then this community is stored, and the corresponding nodes are removed from the graph, and then the whole procedure is just repeated for the remaining graph until there are no more communities left. And the GB2 is at its core just a recursive binary separation of the graph. Then the quantum providers have been IBM, for the GB1 and GB2 with the Qiskit software development kit, and D-Wave with the Ocean software tools for the QA1. And yeah, then we have defined a deployment model and implemented a code generator based on Xtend, and the Eclipse series has been used as a graphical modeling environment. So what are now the lessons learned from the small demo case? First of all, in our case, we have utilized very problem-specific algorithms that have been known to us in advance. But this raises the question of how to do a proper mapping between a problem at hand and the available solutions to that problem. This may also need a proper orchestration of modeling and the potential algorithms together with data structures and complementary classical tools. Then the second point deals with the question of how to model algorithms utilizing such quantum elements if no one is available yet, as it has been in our case. And if such a new algorithm has to be designed, one has to consider potential trade-offs. Shall it be more generic and modular, or shall it be more specific and useful for the particular problem? And a possible solution for this would be to replace the generic parts of an algorithm with the specific ones based on the knowledge about the problem and the backend, in the sense of using refinement models. And then when it comes to the problem inspection, different vendors use different tools, which also raises the question of how to perform the abstraction step to model-driven engineering in this context. And what we've also noticed is an increase in efficiency when it comes to experimentation with the various approaches. The next point considers the fact that our proposed model just considers one single task, but in a more generic and holistic approach, according workflow models and the orchestration tools would be necessary to represent the whole task chain. And lastly, we recognize that not only model-driven engineering can be applied to quantum computing, but quantum computing can also be applied to solve hard MDE tasks. So for example, we have recognized that the community detection problem can be projected to the modularity maximization problem in software engineering, where one wants to have a big system being structured in modules in such a way that the coupling between the models is minimized and the cohesion within the models is maximized. Okay, so based on the demo case and the lessons learned, I want to continue now with the research roadmap and some resulting challenges and research questions. And in this context, the first thing I want to mention is that a holistic MDE approach would require a way to account for the quantum data transformations and especially the modeling of quantum algorithms themselves, besides just applying the existing ones like we did. But there's also the question of how to consider hybrid algorithms, which are especially promising in the current NISQ era, and which extensions in modeling languages are necessary for this purpose. Furthermore, when it comes to code generators, these rely on patterns and standardized ways to represent certain problems, and they would require repositories of quantum and hybrid algorithms together with optimized procedures to select and apply these elements. And this also raises the question of how such processes can be modeled and reused in a code generator. Then the third research question deals with the cloud-based deployment of quantum computing. And here, maybe existing modeling languages for cloud computing have to be extended to account for the deployment and the integration, especially of such hybrid algorithms and the peculiarities of the different quantum machines. Then for creating executable DSMLs, the problem of testing and debugging is very important. And it's even more complicated for the quantum computing domain because any measurement during the computation would destroy the superposition state. So it's difficult to gain information about the state during the computation. Then, as I said, different vendors offer different tools for the problem inspection. And the question how to perform the abstraction step is an important one to ask in the future. Then the fifth research question refers to increasing the efficiency of experimentation with quantum technologies via MDE practices, like, for example, an automated data generation from models. And therefore, the modeling environment may serve to run domain-specific studies on quantum computing technologies, provided, of course, there are feasible DSMLs for this purpose. And finally, the last research question does not ask how MDE can be applied to quantum computing, but rather how quantum computing can help to solve hard tasks in model-driven engineering, like, for example, in model transformations or in model-based optimization. So to summarize, we've shown a small demonstration case for applying model-driven engineering to the quantum computing domain via dedicated problem-oriented DSML for the community detection problem. And we've presented some resulting challenges to further explore this topic. And in this sense, we would now kindly invite the community, you, to take the next steps together and build according repositories for such model-driven engineering applications. And these would include, on the one hand, exemplar templates, like the one outlined in this presentation, to explore how to apply MDE on a conceptual level. And on the other hand, there would be also reference applications that serve as specific implementations and therefore as a basis for further abstractions in a sense of model-driven engineering. So what will be our focus, our future research? Our focus will be still on the problem domain. So we will go into the direction of constructing a DSL and workflow models, especially for the domain of quantum combinatorial optimization, especially on the current NIST devices. Yeah, with that being said, I thank you for attention, and I'm looking forward to the discussion part. Thank you.
Thank you, Felix. Thank you, Antonio. And Manuel is also here, by the way. I haven't noticed in the beginning. We have a question by Ina. Ina, do you mind asking the question yourself?
No, I'm very happy to do so. Hi, welcome. Hi, Manuel. Also interesting to see you here in this area and to hear about MDE and this kind. Very interesting talk, also very interesting research idea. I'm wondering about the level of detail. So if I look at classical MDE, right, what we do is we model sort of things from the physical world like entities, and then we try to generate code. So usually, I mean, a standard example would be modeling something like a database system, students, teachers, what have you, and that's then classical MDE. When I look at quantum algorithms, I see that they are all on a very fine grain, right? We are manipulating single bits and we are sort of tweaking stuff around. So we are on a sub-method algorithmic level in that sense. And I'm wondering how you envision bridging that gap. So maybe first question, do you also see that gap, or am I wrong here? And then are you envisioning specific modeling concepts that are actually quantum? I mean, also what I've seen in the talk before seemed like classical software structure, but what makes modeling quantum? And maybe that's a tricky question. We actually don't know how to answer yet.
Yeah, it's a good question because, yes, quantum computing is still in a very young phase, and many people advocate for breaking the abstractions so you can really have pulse control, that you really optimize what you want to do. But if we look at approaches or services from, for example, IBM, they offer routines where you can treat everything kind of a black box and use it and have abstraction steps. And then you can utilize this within an MDE approach. And what we are thinking of, for example, is kind of a mixture. So when we are talking about these workflow models in our future research, it's not just taking already finished algorithms and applying them to a problem like you would do with any other algorithm. It doesn't have to be quantum, but it's rather about how all these steps, which are very often the same. For example, when you have a variational quantum algorithm, you start with defining your objective function and then deciding on your classical optimizer and so on. There are very often similar steps, and these can also be abstracted, and here MDE could help. Hope that answers the question a little bit.
Yeah, thank you.
Okay, so any other question?
this is Elisabetta Di Nitto. First of all, thank you for your nice talk. It's been very interesting. Sorry, it seems that my camera doesn't work, so I hope now it works, yes. My question is, of course, as you said, we are at the beginning, so it is, and your approach is quite, if you want a long-term one, in the sense that you are envisioning a situation in which your model-driven approach will exploit essentially these building blocks that are built from this quantum mechanism. But did you have the opportunity to experiment in practice, besides the specific case study that you have shown about the network, and check whether also from the perspective of users who are not, I mean, yourself, I mean, the developers of the approach, if from this perspective, your approach is helpful as opposed to using what is already available as lower level building blocks in the quantum context?
So you basically mean the benefits of using the MDE practices instead of just applying the existing algorithms?
Yeah, in this specific case. And so what would be, as you said, we are the idea is to use these building blocks to raise the level of abstraction. What do you think we gain from this, and the end users gain?
Yeah, so actually in our case, we have written the algorithms that we've used on our own prior to this. And from the point of view of the user, it would be easier to have kind of a model that shows these building blocks and shows how to develop quantum algorithms, or these hybrid quantum algorithms, and to put away all the vendor specific things. Like, for example, when I want to solve some problem, for sure I can look at the Qiskit library if there are existent functions, routines, or methods for this particular problem. But to have all these things more portable and hardware and vendor agnostic, I think here the abstraction would be necessary, and also for experimenting with various approaches. For example, if I say, okay, I want to develop a new algorithm and I want to experiment with different backends, but without really having to learn new programming languages or having to learn all the specific things, I can just experiment with this approach more easily when I have it just as building blocks.
I'm wondering whether we shouldn't consider also the possibility to include into the modeling approach aspects that concern let me call them non-functional characteristics of the various species that we use. So, for instance, a certain algorithm running on a certain cloud node will behave differently as opposed to the same algorithm running on a different node with different characteristics. So I'm wondering whether also this kind of things could be useful, for the information about this kind of thing could be useful to the end users and could be somehow help the end user in understanding what to do and how to use the various elements that the user sees in the modeling framework.
Yeah, this is a very good point. Manuel is here, the first author of the paper. Yeah, I think this is something we should also incorporate in the future.
Okay, great. Thank you very much. Very interesting work.
Thank you, Elisabetta. Is there any other question?
I can ask maybe if there is no from audience.
Go ahead, Shaukat.
Yes. Yeah, thank you. Thank you for a very nice presentation and a very nice way of presenting this model-driven engineering and quantum computing. So I was wondering about, we also saw in the previous presentation about using UML activity diagrams, and in one of our previous work, we tried to model UML state machines, try to capture this, this quantum software states, but it got too tricky, especially even with a simple program. When I tried to do this exercise to use, for example, OCL to model state invariance on UML state machine, they become very difficult to model. So what do you think? One thing I see is that, for example, we can use, for example, bracket notation from quantum physics domain and try to mix it with somehow on UML state machines, but I found that that was very difficult for software engineers like us to understand. And when I try to use OCL to model similar thing, it doesn't go very well. It got too out of hand. So what do you think about, it's just an open question, I think, for us, is that if I have to model these kind of constraints and states, abstraction on the states for quantum programs and quantum software, how do you view how it should look like, or it should be based on OCL or something, a mix of bracket notation plus OCL or something maybe totally new? How do you view, maybe, yeah.
I would say that, hi, I'm Antonio.
Hi.
I would say that from our point of view, I'm with you, right? If you start looking for state machines, if you try to apply some higher level UML concepts, probably would be rather complicated. But that's why we are trying to focus on DSMLs and DSLs in the sense that we can have just very specific, try to make a compact language and that can fix very well to this domain of quantum computing. So in this sense, also we can rather, let's say the quantum experts can also understand. Probably quantum experts, and they are not used to use state machines, but they will be very glad if they have something more similar or where they're used to work with, and something also that give us something a high level programming, that so to say. So so we are trying to do some research in this direction, trying to implement or do some kind of DSLs.
But do you view those DSL to be similar to what we know as a software engineer, or do you think it should be something quite different?
How something quite different? I don't get it.
Do we?
Maybe it's more like what the domain experts are already using. It maybe not necessarily the software engineers, but the domain experts. If we think about chemistry or other disciplines, where you would like to use quantum computing, and you have already some notations or some formalisms, and then maybe you can reuse these formalisms, and then we would put, let's say, this intelligence to come up with a quantum program somehow in the code generators.
I see. Yeah. Good. We just need to find quantum physicists and software engineers work together somehow.
Yeah. Indeed.
Yeah, that's all from my side. Thank you.
Okay, thank you.
I think there is a question by Yakov. Yakov, you are muted.
Right. When I represent a system by a Laplacian matrix or a density matrix, I am proposing a way to solve a problem. And the problem is, for instance, modularization. So, what I'm not sure I understand in the last lecture presentation is what is the problem that you are trying to solve. What MDE serves to in order to solve a problem.
It's if may I answer, it's rather about easing the way to use quantum computing for own experimentation. So if you leverage it on, or if you take it to a higher level and just utilize building blocks as it is done in MDE, it's more easy to do experiments and so on than really digging into the details of the material.
But this
it's
is
like sorry, it's like classical programming, right? Let's put it this way. I mean, in the 50s and 60s, you start working with the ensembler, right? And you have to move AX to BX and try to program, but that was very difficult, right? And there was a level of abstraction in the case that we right now just everyone works with object-oriented programming. So now in quantum computing, we are in the same level, so to say. You have to quantums working with qubits, which is very difficult, very complex for anyone who maybe is not physics or an expert in the domain. So what we're trying to do is to try to hide the level of abstraction with less code, like in object-oriented programming. And with this less code, we're able to generate code specific for the quantum specific programming language, right?
But as long as the classical programming is not formalized, you have no assurance at all that you are not making errors, bugs, or whatever. So I would expect that not to go the same way in quantum software systems as we have done in classical software systems, that the problems are real now. Whenever you have a very big system, a classical one, you have no assurance that you are not doing serious bugs or logical problems. So I expect that we should, from the very beginning, to formalize in order to solve problems. Define what is the problem that you are solving. Then, okay, I expect something from your proposal. Have I understood?
Yes, and I fully agree here. So a formal basis is very important, and MDE is not per se contributing to this formal basis. You are fully right. So this formal basis is very important. And then maybe what model-driven engineering could contribute to in the future is that if you have certain patterns or best practices, that you can utilize these best practices in order not to make mistakes. But this is, as you have said, the next step. A formal basis is very important, and this is also very important to build up a model-driven approach here. Yeah.
Thanks.
Okay, so are there any other questions? So if not, this concludes this session. Thanks for for the presentations and all the authors for having submitted. Now we have a break, a 15 minutes break. I will not close Zoom, so I will have just this slide here for the break. So we'll be back in 15 minutes, which is at 5 o'clock Central European time. Yeah, once again, thank you all for the speakers, and this concludes this session. See you in 15 minutes.
Hello? Yes, so...
All right, let me stop my share.
So do we have speakers for the next 2 talks? Experimenting with discrete time quantum walks and generalized quantum tree.
Yes, sir. Can you hear me?
Yes.
Good evening.
So you are the first author, first paper, right?
Yes.
Okay.
And
That's
also
cool.
Elisabetta Di Nitto that is here.
Yeah, I can see her in the list too. Let's see, for the second paper, do we have authors here? Probably not, so I can try to get ready the video. Maybe they will appear maybe at their time, maybe, so we can wait, but I can keep video ready.
Pier Ricardo, I think you can share your screen now. I have made you a host of the meeting.
Yes, thank you.
Yes, so I think it's 5 o'clock, so please go ahead with your talk.
Yes, can you see the video?
Yes.
Perfect.
It's not yet full
Okay.
screen.
Okay, just a moment. One second. Can you see it now?
Yes.
Okay. So, everyone, my name is Pier Ricardo Olivieri. I'm here to present our work made in collaboration with Manoush Skarpour and Elisabetta Di Nitto about an experimental implementation of discrete time quantum walk using the IBM Qiskit library. Just a few words about us. Elisabetta Di Nitto is a full professor at Politecnico di Milano. Manoush Skarpour is an adjunct assistant professor at McMaster University. And I am Pier Ricardo Olivieri, still a master student of computer science and engineering at Politecnico di Milano. So, aim of this paper is to provide our implementation of 2 quantum walks model for a cyclic graph with 8 nodes, namely the Coin quantum walk and the Szegedy quantum walk. For both of them, we extracted the circuit from literature. Then we provide an implementation using the IBM Qiskit library. And we run an experiment both in simulation and with the real IBM quantum computer, showing the results that we obtained. So random walks are a stochastic process that consists in successive summation of random and independent variables over a mathematical space. They exist in 2 types: discrete time if time belongs to natural set, or continuous if times belong to the real set. Here our focus is on discrete time. Below we can see a picture that is an example. We can see the line of the integer number, positive and negative, and we have our walker that is currently in position 0. Now what we want is to perform a random experiment that could be, for instance, a coin toss. And depending on the outcome of this random experiment, we want to move the walker on the left or on the right. We can achieve that by increasing the position or decreasing it by 1. What we obtain at the end is, by repeating these steps, we obtain a random path over this mathematical space. Quantum walks are the analogous of random walks. And again, our focus is on discrete time quantum walks. But in this case, each quantum walks define its components, as we will see in the next slides. So we can start with the first model, that is the coin quantum walk. On the right, we can see the cyclic graph with the labels of each node. And we can define the elements that compose the coin quantum walk. First, we have the position that is represented by vector of 3 qubits. We need 3 qubits in this case to encode our 8 nodes in a binary way. And the labels are here near the nodes. The coin in this case, so our random experiment, is a vector in a 2-dimensional Hilbert space defined by the cat0 and the cat1 here, HC. Then we have the shift operator that increase or decrease the actual position of the worker by 1, and the mathematical space in which the worker move is defined by the Kronecker product of the Hilbert space of the position and the Hilbert space of the coin. Finally, we can represent the coin quantum work operator as a single operator U defined by the shift and the coin operator. So this is the circuit that we implemented. Here we can see the last 3 qubits representing the position of the worker. The first qubit is for the coin. And here we can see these 2 sub-circuits, the increment circuit and the decrement circuit. They basically form the shift operator, and one increase the position and the other one decrease the position by 1. Only one of them can be activated, and we decide this by the outcome of our coin, is the Hadamard gate coin. So we choose the Hadamard gate coin for its simplicity. We just have to apply an Hadamard gate. And in literature, we can find also different type of coins. Then we have our increment circuit. This is composed by succession of controlled and multi-controlled gates. Its behavior is to increase the actual position by 1. And in the right, we can see code in Qiskit to implement it. It's very simple. We have a succession of controlled and multi-controlled gates. It is worth to mention the function MCP that is used to build controlled gates with more than 2 controls. Here we can see the argument of the function that are the controls, the target, and the mode, that in this case is no ancilla, and we will see later why this is important. Then we have the decrement circuit that is very similar to the increment circuit. They decrease the actual position by 1. And now we have negative controlled and multi-controlled gates that are basically obtained by negating the control before and after with the NOT gate. So this is the final decrement circuit. As we can see, also the code is very similar to the increment circuit. We just added the NOT gates. And this is the final circuit. The links for source code and the QX simulation can be found in our paper. And now we can discuss about the results that we obtained by performing 5 experiments. In the right, we can see a picture of an averaged picture of the results that we obtained. We used as a backend the IBM Q Athena. We choose this one because we need at least 4 qubits. And IBM Q Athena provide 5 qubits with the highest quantum volume given our account type. We choose to perform 1 step of the work. And here in the right, we can see the results that we obtained. In the x-axis, we have the labels that represents our nodes. In the y-axis, the probability to find the worker on a given node. And with the black bars, we can see the simulation results. Indeed, we have a 0.5 probability starting from the position 0 to move in node 1 or in node 7. White bars instead represent the real simulation on the IBM quantum computer. We expect to find the 2 highest probability in the correspondence of node 1 and 7. Here we have the highest probability on node 1, but unfortunately we have the second highest probability on node 3. So this is an outlier, and we assume that is due to noise. Also in node 7, we have the third highest probability, but still we have this outlier. Now, what about generalization of this model? Basically, we implemented a specific graph, a specific circuit for a cyclic graph with 8 nodes. And so we can ask how to scale with quantum walks. We can scale with respect to graph family, for instance. In literature, there are examples about circuit for torus and complete graphs. And to construct this, we need to alter the circuit accordingly. Or we can also scale with respect to graph size. Again, we have to alter the circuit accordingly, but in this case, this comes also with a cost. Increase the size of the nodes means to increase also the multi-controlled Toffoli gates, and this means to increase also the resources, as we will see in the next slide. Here, we can see how to build multi-controlled gates with more than 2 controls. In Qiskit, we used the function MCT, and here we report 2 approaches found in literature, just to show how complex is when we have to increase the number of nodes. Basically, we have here 2 approaches, the one of Nielsen and Chuang that uses ancillary qubits on the left. And here we use 4 ancillary qubits that are only used to construct the gate to construct a 5 controlled gate. In the right, sorry, we can see instead the approach of Barenko et al. Now, this is an example with 3 control multi-controlled gate. And as we can see here, this is a no ancilla approach. So we don't use more qubits, but we scale in depth. Both of these approaches needs more resources. So this is why it's for now it's problematic to construct a circuit with a lot of nodes. And now we can talk about the second model, the second circuit, that is the Szegedi quantum walk. The Szegedi quantum walk is a quantization of a classical random walk of Markov chain. And now the walk occurs on the edge of a bipartite graph. Bipartite graph that is obtained by the initial cyclic graph with 8 nodes by duplicating the nodes in 2 sets and connect each node with its neighbor in the opposite set. We will see an image in the next slide. Now we just define the elements of the Szegedi quantum walks that are the state vector. It is our position composed by 2 vectors R1 and R2. Then we have the main operators of the Szegedi quantum walks, the swap operator and the reflection operator. We didn't report here for simplicity because they are kind of complex. So interested readers can find them on the paper. Our mathematical space now is defined by the Kronecker product of H1 and H2, respectively the Hilbert space of register R1 and R2 that are both of dimension 3. It is the number used to encode our nodes. And again, like for the quantum walk, we can express the one-step Szegedi quantum walk operator with U that is given by the swap operator and the reflection operator. Now, the graph representation is given by the adjacency matrix A. It is then used to build the transition matrix P that represent the transition probability of a node to its neighbors of the graph. Here in the right, we can see the bipartite graph obtained by duplicating the nodes and connect each node with its neighbors on the opposite set. And then we can define now the initial state of the walker that is given by a column of the transition matrix P. In this case, we represent phi0, that is the node 0. Indeed, we can see that we have an equal probability to move on node 1 and in node 7. This state is prepared on register R2 before the circuit. We can prepare it using an Hadamard gate and a controlled NOT gate. And the expected output is given in register R1. And in this case, we expect an equiprobability of the adjacent nodes. This is our final circuit for the cyclic graph with 8 nodes. At the end, we can see our swap operator. Now, the first 3 qubits represent register R1. The last 3 qubits represents register R2. And this part of the circuit in the middle is the reflection operator. Again, the links of source code and the Kirk simulation can be found on the paper. And now we can talk about the results that we obtained with the Szigeti quantum walk. Again, we run 5 experiments. In the right, we can see the averaged results obtained. Now we used as the backend the IBM Q Melbourne 16. We choose this one because given our account type was the only backend with at least 6 qubits. Is the minimum requirements for our instance of the problem. And this backend provides 16 qubits and a quantum volume of 8. Again, we performed just one step on the IBM quantum computer. On the right, we have a similar structure of the previous experiment. We have on the x-axis the nodes, on the y-axis the probability to find the worker in a given node, and in black bars we have the simulation that in this case is again starting from the node 0, is again 0.5 to find the worker in position 1 or 0.5 to find the worker in position 7. But now, unfortunately, the results that we obtained for the real simulation doesn't match our expectation. We have a lot of outliers and the results are very bad. Assuming that our implementation is correct, we assume that is due to noise. So now to conclude this presentation, here we wanted to provide our implementation for these 2 quantum walks model and share the results that we obtained with the IBM quantum computer. But this is just this work is just a starting ground. Our initial idea was to build a library for a quantum walks model to wrap the complexity of build this circuit. And for now, we just use this work to experiment and to gain knowledge on this field and to understand the limitations, because at the moment we have important limitation both on the resources and on the noise in the current available quantum machine, at least for our experience. This, I want to end the presentation, and I thank you for your attention.
Thank you very much for your nice presentation. So now we have time for some questions. So first question is from Raikov. Yes, you are mute.
How easy is to generalize your graphs to any graph? Because your examples were either circle or bipartite or complete, but not something totally generic.
Yeah, for the moment in literature, we found only simple examples of graphs. And I think that this is also due to the actual limitations. Just to run one step on a cyclic graph that basically is really simple. It's a very simple graph. We had a lot of noise. We experienced a lot of noise. And so I think that now maybe we have this small implementation for specific graphs. And maybe in the future, we can generalize with respect to bigger graph or generic graph. But this is just my hypothesis.
I'm asking this question because one recent trend in neural networks is to make convolutions on graphs of any type, not only sequential or grids. And maybe your work is some beginning of something in the direction of some simulation of simple graph convolutional networks.
Yeah, the main objective was to build this library, also to prepare something for application in deep learning. I saw something in literature about application of quantum walks in deep learning, and yes, I hope to be able to continue this work and to provide something for bigger applications.
Thank you.
Thank you.
Yes, so we can take a few more questions if anyone has any discussion points.
How big are the applications that you can solve at this point?
At this point, given our account type that is the free account provided by IBM, we tried to solve this problem that is presented in the paper. So a cyclic graph with 8 nodes and just one step. So for now, the results are, the application are for very small graphs.
Mm-hmm.
And the noise is very high, and probably probably it's better to experiment with a more powerful quantum machine to understand the real limitations.
Right. Have you played simulated different levels of noise or not?
Yes, this is why we average the experiments, and we also have to try with different backends. But now this was we have a constraint because, for instance, as already mentioned in the presentation, for the Szegedi one, we just have at our disposal just one backend, and for the other approach, we have at our disposal more backends, but with less resources. So for the moment, we have a strong limitation that also in the noise that we perceive during the experiments.
Right. Thank you.
Thank you.
Yes, any further questions? Okay, then we got email from the last authors. So first, we'd like to thank you for your presentation, and then we move to the last talk of this session. And so they will not be able to make it. So I think we have to play their video, and then we continue. So
Thank you very much. Bye.
Thank you. So shall we start at 5:30 or at the planned time, or we should play now?
I guess we can start now, right? And then we just finish a bit early.
Okay, then I will play the video now.
Yeah.
Hello, today I'm going to talk about quantum algorithms for research. This is a fast abstract, so I'm going to be reporting on ongoing research. So let me go to my slides, and I hope you enjoy the talk. Okay, let me just start by trying to motivate you towards studying quantum algorithms for research. Now, research algorithms play a crucial role in many applications, particularly in artificial intelligence. So, research algorithms appear in many different domains: game-playing systems, production systems, robotics, optimal planning, as it is called. And so, in the language of artificial intelligence, an agent performs reasoning by exploiting some knowledge or some previous knowledge about a given problem. And so tree search consists of one such form of reasoning. Now, at the bottom, you see a simple binary tree search, and at the bottom right, you could see a different tree search algorithm. It is called Monte Carlo tree search algorithm, and it is widely used in reinforcement learning applications. Now, what about Q motivation, the quantum motivation? We all know that Grover's algorithm can give us a quadratic speedup in searching unstructured databases. And so if we could map quantum search techniques, Grover's algorithm and all of its variants into a quantum tree search technique, maybe we could enhance some of the tree search algorithms. Now, another interesting topic is amplitude amplification. Amplitude amplification is some form of a quantum heuristic. And so at this point, I will leave you with a question that I find very interesting, which is, what about quantum informed tree search? Maybe amplitude amplification has something to do with this. Now, at the end of this talk, I will try to answer this question. Okay. Now, the rest of the talk will be as follows. Firstly, I will briefly talk about classical tree search algorithms. Then I will talk about the state-of-the-art of quantum tree search, and then I will report on ongoing investigation about generalizing quantum tree search, and I will clarify what I mean by generalizing. Now, at the end of the talk, I will refer to some new ideas that we've been working on, and maybe we could discuss them afterward. Okay, let's start by classical tree search then. Now, in tree search, the goal is to find a sequence of actions that lead to a goal state. So we start in a given node, and we have a goal state that we want to reach. And so we need to find the optimal sequence of actions. Now, given that we don't know anything about the structure of this tree, in the most general form, the complexity will be the branching factor B to the depth of the tree, D. So at this point, another interesting question arises, which is what happens when we have a tree with non-constant branching factor? Okay, when we have non-constant branching factor trees, using the maximum branching factor no longer makes sense, right? And so in these cases, we should use the effective branching factor. It's known that the effective branching factor converges to the average branching factor. And so in these cases, the complexity of finding a goal state is the average branching factor exponential with the depth of the tree. Now, at this point, another question arises, which is, can we do better than brute force search? So can we exploit some knowledge to find a goal state in less time? And this leads us to informed research. Now, in informed research, we exploit previous knowledge from the problem, some given knowledge about the problem, and we expand the nodes that verify some criteria. Now, we use some heuristic function g of n, and so for example, for the traveling salesman problem, g of n could be the distance to destination. So in informed research, we prioritize over what nodes we expand. And so for the case of traveling salesman problem, we expand the node that is closer to the goal state. Now, in quantum tree search, the main difference is that the agent now has the ability to perform actions in superposition. And so what we need to do is to map an action into a quantum state. For the tree in the left, we see that we have a branching factor of 2, and so the quantum state that represents an action for the first level of the tree can be represented by the uniform superposition over action 0 and 1. Now, the quantum state A0 represents the uniform superposition over all possible actions to take at level 1 of the tree. But in general, we want to be able to run over all possible paths of the tree. And so we can add multiple quantum registers for different actions. And so we can build the quantum state A that will be the tensor product between all possible actions. Now, at this point, to discover the optimal sequence of action to reach the goal state, we're basically in the same paradigm as in the original Grover's algorithm. And so we just need to have an oracle that is able to mark that correct sequence of actions. And so now the goal is to reach the goal state. Now, the goal is to amplify the amplitude of that correct sequence of actions. So the sequence of actions that lead to goal state. And so all we need is an oracle that signs that correct sequence of action. Okay, again, our oracle will invert the phase of the sequence of actions that lead to the goal state. Now, we build the uniform superposition over all possible sequence of actions until a depth d, which means that each sequence of actions will have a corresponding amplitude, which will be 1 over the square root of a to the d. Now, we can look at the quantum state A, the uniform superposition over all possible actions, as being spanned by the subspace of good actions, which means the correct sequence of actions, and being spanned by the subspace of bad actions, all over possible sequence of actions. So following Grover's algorithm, we know that applying j iterations, the amplitude of the correct sequence of actions will be amplified. So now the goal here is to find the optimal number of iterations. We know that theta is the arcsine of 1 over the square root of a to the d. And so if we solve for j, we can see that we need the square root of a to the d iterations in order to reach the optimal sequence of actions. And so the square root gives us a quadratic speedup compared to the class counterpart. Now, an interesting question arises, which is what happens when we have non-constant branching factor trees? When we have non-constant branching factor trees, we know that the effective branching factor converges to the average branching factor. However, in the quantum setting, we cannot use the average branching factor. We must use the maximum branching factor always, because we don't have a way of distinguish what action should we take at what state. And it turns out that Grover's algorithm can no longer guarantee a quadratic speedup in all cases. Specifically, when the average branching factor is greater than half of the number of superposition terms, then Grover's algorithm provides a speedup, and in the opposite direction, Grover's algorithm can no longer provide a speedup. Now, let's talk about generalizing quantum research. Now, by generalizing, we mean that we need to use Grover's algorithm to provide a speedup for all non-constant branching factor trees. Now, the solution to deal with all possible non-constant branching factor trees lies in, instead of representing only actions, we can represent the node as well. So instead of using the quantum state A, which is the tensor product of all possible sequence of actions, we could have the state psi, which is the tensor product between the node and the sequence of actions. And this allows us to create a superposition over the set of admissible actions to a given node, instead of just creating a superposition over all possible actions. Now, how can we create the superposition over the set of admissible actions to a given node? Now, let A sub s be the subset of admissible actions to a state S. We can see in the tree in the left that for the node S0, we have that admissible actions are A0 and A1. And so we can build a quantum operator A that receives the current node and an action register initialized in the ground state, and maps that action register to the uniform superposition over the set of admissible actions conditioned on the current node. Now, once we have a quantum operator that prepares the superposition over the edges of the tree, we need a new operator, S, that acts as a state transition operator. So this quantum operator S will guarantee that when we receive a state action pair, we can map the state to the correct next state S prime. And so, interleaving A and S for a depth D, we can create a superposition over all paths until depth D. And now we just play the same game as before, right? Just need to build an oracle that inverts the phase of the quantum state as the correct goal state, and then apply j iterations of the Grover's algorithm in order to amplify the amplitude of sequence of actions that lead to the goal state. And once we solve for j, we find that we need the square root of the average branching factor to the d in order to reach the optimal sequence of actions that lead to the goal state. And so this way, we have a quantum algorithm that solves quadratically faster for the optimal sequence of actions in any type of branching factor tree. Now, there are downsides, of course. So the first downside is that we need to double the number of qubits needed compared to the first quantum approach. And the second one is that the quantum operators, A and S, are controlled operations. And so this means that the number of gates will increase exponentially in the number of qubits, and this could lead to a poor performance, at least in the current state-of-the-art of quantum computers. Now, to end this talk, let's give some new insights on quantum-informed research. Now, in the beginning of this talk, we said that amplitude amplification is a form of a quantum heuristic. And so, consider the interesting case of Grover's algorithm when we have n/4 marked element. In this case, Grover's algorithm needs a single iteration to read a marked element with certainty. And so, consider the following example. If we had 4 actions, and so we build the uniform superposition over 2 qubits, and if we want to collapse this state into the action 1,0, Grover's algorithm needs a single iteration to read this state with certainty. And with this, we have two interpretations. First, this could be interpreted as performing pruning. And a more interesting point is that now we could use an oracle that marks an action that has the highest score following some metric, and this could be some quantum greedy best first approach. Now, this technique only works for the case when we have a such space of n elements and we have n over 4 marked elements. Now the question is, how can we generalize this to an arbitrary such space and an arbitrary number of marked states? First of all, we could use an oracle to select 25% of the entire such space based on some magic, and then use a single Grover iteration, collapse the quantum state, and see if we reach the optimal sequence of actions that lead to the goal state. Or we could apply exponential search instead. And more interesting, we could perform the same thing again. So we could recursively select 25% of the search space, and maybe this will give a recursive quantum search algorithm. It is, I finished my talk, and let the discussion begin.
Yes, so I think that was the talk. So I think if someone has questions, they may like to send it to the authors since they couldn't make it today. So I think this is what we have in our agenda today. And then tomorrow we will start at 1 o'clock. So it's 1 hour earlier than today because of the second keynote. And we will be using the same links, YouTube and also this Zoom link. And that's all for now, I guess.
That's right. Yeah. Okay. So see you all tomorrow.
See you all tomorrow.
Okay. See you tomorrow.
Bye-bye.